This is an introduction to VLSI design, and today we will talk about an in-depth introduction to this class. In this class, we will talk a lot about integrated circuits, or ICs, which basically have many transistors accumulated on a single chip. The word VLSI is abbreviated as a very large scale integration, which means you have a bucket loads up to the point of billions of transistors in a single design. We will also talk about complementary metal oxide semiconductors, or the CMOS, because it's fast, cheap, and it has low power consumption properties. We will also focus on how to build your own simple CMOS chip using CMOS transistor. So you need the knowledge of how to build logic gates starting from transistor, which means that this is a bottom to top design. We will also dig deep inside the transistor layout and fabrication, which will show you the reality of what's inside the chip. The rest of the course is basically focused on how to build a good CMOS chip, with more emphasis on the good part. As you can see here, this is a chip with many blocks. Each block has its own specific job. And in this design, or this is a CMOS design for the famous inverter, which is composed of two transistors. We will see or check this design in detail throughout the course. Where does the VLSI class fits into? You've seen this picture. We have a software part and a hardware part. And there are courses that are designed to teach you about the operating systems, or the system softwares, the compilers, and the other parts of softwares. There are also other courses that are specialized on hardware, like having the courses focused on the instruction set architecture, or the ISA, which is the blue rectangle that is between the software and the hardware. It also tells you what are the instruction sets, procedures, how to write down assembly language code that is very close to the hardware, also the I/O system. This course is usually the computer architecture or the computer organization course. And we have other courses that are designed for data path and control and digital design. Also, we have our course, the VLSI design, which is focused on the transistor level, which is the level at the end of this figure. This is a very low level, which is basically the simplest switches of the hardware, which represents either having a 0 or a 1. So we will start from the transistor, and in your project, you will start building up to circuit design and digital design. This means that in your project, you will adopt a bottom to the top approach. So you'll start from transistor, building up gates, and from gates you collect them together to build a simple block. And from this simple block, you will have bigger block to have up to the subsystem, and maybe up to the system. And also in your project, you will see how the data path and control interchange the information and data from input to output. Now, here's some history. You can see that this history goes back to the previous century. We start from 1898 all the way up to 1997. Here you can read all of these, and you have icons below to remind you what's going on. But here we want to focus on three scientists, which is those scientists, Dr. John Brandeen and Dr. William Shockley, and we also have the Walter Brattain, which is basically the supervisor of those two doctors. Those three are the one responsible for building the first transistor ever. And if you can read below, you can see that in December 16, we have the invention of a point contact transistor, which is the first transistor. That was in, as I said, 1947. And they built up on that. And in 1950, transistors started to be developed at Bell Labs. And from the transistors, the idea start to build up to the computer that we know today. So you can see here, for example, that we have the first mini computer in 1960, and we have the famous Moore's law. Moore's published his paper at 1965, and he was predicting the rate of growth of the integrated circuit. And after this, as you can see all the way down, in 1989, we have the World Wide Web, which is the internet and what we see today. And after that, one of the famous old transistor, which is Pentium, was developed in 1997 with 7.5 million transistors. So it's quite the jump from 1950. After 50 years, in 1950, we have few transistors. In about 2000s, we have about 10 million transistors in a single chip. And you can, in the current time, we have up to billions, actually, of transistors in a single chip. As I mentioned, that the initial electronic devices were vacuum tubes until 1950, and in 1950, we started to develop transistors. So the transistor was invented in 1947 by John Brandeen, William Shockley, and Walter Brattain at Bell Laboratory. In 1956, they received Nobel Prize for that. Those are the three gentlemen, and this is their transistor that they invented at that time. Every electronic application requires a circuit, and the circuit is basically consists of a number of devices like transistor, diodes, resistors, capacitors, inductors, etc. In 1960, a technology was developed by which an entire circuit could be fabricated on a single piece of silicon. And this is what we call an integrated circuit, or IC, or simply a chip. That was the beginning of the of this class, sort of thing. The generation of ICs, till now, many generation of IC has come up. We started with SSI, and then from that we moved to the MSI, and then LSI, and then we end up with VLSI. Of course, we have others as well. But since this course is an introduction to VLSI design, we will stop at this level. The S here is for small, the M is for medium, and the L is for large, and the VL is for a very large scale integration. There are so many technologies to build up transistors. The commonly used IC technologies are the bipolar, the MOS, and the CMOS. The MOS or the has two types, the NMOS and the CMOS. The CMOS is being the most common today, and that will be the focus on the starting of this class. Later, we will talk also about the NMOS design. The MOS, or simply the metal oxide semiconductors, and some people like to call them MOSFET, or the metal oxide semiconductor field effect transistors, is basically consists of or composed of two types, the NMOS and the PMOS, where the voltage applied to an insulated gate and which controls the current between the other two terminals, which is the source and drain. And as you can see here in the figure, you have three terminals. This is the gate where you have the control, and the source and the drain, the current will be moving between those two terminals. This is a real one, and you have the three terminal as well. The low power allows very high integration. So that's always the goal, is to have the low power consumption, which implies having a very high integration. There is also another very important goal, which is the speed. Unfortunately, there is a trade-off between those two goals. The most integrated circuits in the 1970s, the processes usually had only NMOS transistor. So there is no PMOS. The reason, it's inexpensive, but unfortunately it was consuming a lot of power when it was idle. In the 1980s up to the present, the CMOS processes are used for low ideal power consumption. So what is this course really about? This course is about very large scale integrated circuit design, as we mentioned. So we need to know the transistors. That's one transistor model. You have the source, the gate, and the drain. We also need to know the interconnects. You can see that the little tiny things here below, these are the transistors that are very similar to what we've seen here. And in the layer in the top of that, we have so many layers. All of them is for interconnections between those transistors. If they, and we will see, we will start by studying the transistors. We will give them like a few chapters to focus on them. And after that, we will move to the interconnections. In this study, we will always look for the area, for the timing, for the power consumption calculations, for noises and what to do with noises, and other topics that we will cover in the coming of subjects. We need to develop models for design and also for analysis. Those models will facilitate for us understanding the transistor and the interconnection. So models are basically an approximation of the real world. We try to make them abstract. And in the modern design techniques, you have it from board to system on chip. And nowadays we have network on chip up to the two-dimension network on chip, and also 2.5 dimension. And now we have 3-dimension network on chip. So we have kind of a complexity problem. So basically, we'll try to divide and conquer to understand them better. We have also simulation and CAD tools. And we will discuss in this course the testing and verification of a complex design. We have also few chapters about the combinational circuit design and the sequential circuit design, but that would be from the from the VLSI point of view. So we will give you certain techniques that you might not have studies in digital design classes. The circuit design, it's an innovative configuration of transistors. So you need to work with these transistors and put them together in a meaningful way so you can perform a specific function better. And we also said that in the previous slide that we will emphasize on the good part or in the better part. And this means smaller, faster, low power, and so on. Smaller area, faster speed, the lower power consumption, and many targets. As you can see, there are so many objectives here. The more objectives that you want, the more challenging the design will be. We focus, or when you design, you focus on ensuring correct functionality first, which means that making sure that this collection of transistors will certainly work, and also we focus on debugging and troubleshooting, which is figuring out why this collection transistor does not work. Usually this happens in verification and testing stages. To do either of these parts, you need to be able to reason about circuits. As we mentioned, we need to know what are the models and how can we take advantage of models in making our problem approachable. So the models are an approximation of the real world. We usually leave out many of the details. It must retain the important facts or details only, which is basically the abstraction. It's an appropriate level, appropriate level depends on questions you want to answer, and you need to be cautious here. The simulation and analysis do not tell you what the circuit does. It tells you what your model of the circuit does. So if you leave something in your model, and when you move to the real thing, and you were implementing the real circuit, it doesn't behave as you expected because you left something out. So you have to make this distinction. So remember, garbage in, garbage out. If your design is not good, the implementation certainly will be a disaster. Some of the hardest work is figuring out the right model for the problem. And usually researchers spend years on this until they find the right model for a certain problem. Fortunately, in our class, one of the famous model of transistor is this one, which is showing you that the transistor have a source, a gate, and drain. You have certain diffusion regions and polysilicon region, and you have an insulator region, which is the oxide or the silicon oxide. That's a very abstract model. And if you want to design any circuit using transistor from this type, we have the CMOS design where you have the network, the pull-up network and the pull-down network. You have also inputs and outputs, and we will come to that later. Here, we know that this is a model and this is another model. What needs to be modeled? We need to model the transistor and the wires as we mentioned. Transistor being the NMOS and the PMOS, and the wires, they are not ideal connector. And so we need to deal with that, and we need to see how complex should the model be to make it more easier to understand. So we will keep the abstraction by leaving out most of the details. However, we will focus on or maintain the real core information that makes modeling the wires or the transistor easier. Resistance affects the supply drops in power lines, for example. We will check also the model or we will model the coupling effect, the inductance, even though we are not going to approach the inductance much. Also, we will check what's affecting this circuit from the outside world, which is basically the environment, such as the temperature, the power supply, and other aspects as well. So there's a lot of subjects that we need to model, and we will see this once we reach to a certain chapter, or we'll discuss something we first need to model it correctly, and then we will jump into the detail and how to make design better. There are many issues that we will talk about, like the functionality, the power consumption, the complexity, the cost, the supply variation, packaging, the yield, short and long-term reliability, timing, circuit noise tolerance, the area, time to market, the testability, the process variation, and the temperature variation. So some of these subjects we will give it more time. Some of them we'll just mention them, and probably some of them will be taught to you in a better course, like business course, for example, the time to market. There are many business courses that talks about this subject. Also, the cost analysis. There are courses that talks only about the cost and how to manage the cost. We will only give a hint on this subject. So, for example, you have a complexity versus correctness and speed in those two examples. So, for example, this one would be easy because it's small. This one, it could be hard, you think. However, both of them are correct. Maybe you would say this one will have more feature because it's bigger. It has this design have many blocks. Each one of them have a specific job, and there is an interconnection with them to give you a certain good information. So probably this would be faster than this one. And each CPU or even a microprocessor, even microcontrollers, they have specific features, and they varies between each others. As we said before, we have a scaling. So this is an example for a small scale integration. This is the inverter. This is the 4049, and there are many versions, but it has only 6 inverters, so it's basically small. The MSI, for example, here we have a counter. This is 74161. And the large scale integration, this is one of the old processor, the Intel 4004, which is a 4-bit or a 4-bit microprocessor. This is the LSI. The VLSI, or maybe more than the VLSI, this is an Intel Core i9 example. And you can see that here, if you look, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cores, and there are multiple other subsystems in the edges that have specific jobs to make the cores work and give you the performance that you are seeking. We have Moore's law, and we said in the history when we talked in that slide with many dates that in 1965, Gordon Moore plotted transistor in his chip, and he had this plot. The paper was published in 1965. So you can see here in 1965, and the years before this, we have a solid line. So it basically was linear. He was plotting the number of years against the number of transistors. But this is a log 2 graph, but that's not the subject here. But you can see that the relation here is linear. So as the number of as the years advances, the number of transistors basically, he found out that the counts or the number of transistors is doubling every 26 months. So here there was real data he was finding out in the real world. And he was getting this data and showing this in the plot. And that was his projection in the future. And he was projecting this for the next 10 years at that time, from 1965 to 1975. And the time showed that he was right. His projection was basically correct. It was doubling every 26 months or so. But there are so many other studies or other people from the other researchers after that, after Gordon Moore paper, they said that it's every 18 months, some of them every 2 years, 24 months, some of them say no, it's 1 year and a half. Anyway, the important part here is that the relation is linear. And you can see that the integration level here, the integration level at that time, the small scale integration was 10 gates, the MSI is 1,000 gate, the LSI is 10,000 gate, and the VLSI was more than 10K, which is basically now we have a huge number. We're talking about billion of transistors. And now continuing Moore's law up to 2020, you can see from 1975, it was plotted in the previous plots, but it was a projection. It was a projection. Here, basically, if you from 1970 all the way up to 2020, you can see that the relation is still linear. If you write or draw a line, you can draw a straight line there, and you can see that by 2020, you have 50 billion transistor in a single chip. Some of the examples here that we talked about, this is the Intel 4004 at that time. And from that, Intel developed more processors up to 8088, 8086, and more versions. The Pentium was very famous at the 90s. And then after that, we jumped to the cores, the dual cores, 4 cores, 8 cores, and so on. And here we have other examples as well, like AMD. We have the Apple, the A7. We have the many other, this is the Xeon processor and so on. So you can see that still the relation is linear. Another conclusion that comes along with the number of transistors is the feature size. We mean by the feature size is the length of the channel that is between the source and the drain, right there. So this length we record in this plot from 1971 all the way to 2021, and you can see that the feature size, which is the length between the source and the drain, is reduced or shrinking every year. It's going down, starting from 10,000 nanometer all the way to 5 nanometer. And right now, in 2023 or 2024, the fabrication and the research, they are talking about 1 nanometer and below 1 nanometer transistors. So here we have this conclusion that the feature size is shrinking 30% every 2 to 3 years. And if you take any two numbers here and you divide them by each other, you would see that the reduction rate, which is what we call S, this S is equal to the square root of 2, which is about 1.4 something. So the frequency and speed impact. We have many other factors that also have a relation. Throughout the years, if we calculate the clock, the speed, we will see that it's growing exponentially. The clock frequency is growing, which means the processor performance is getting better. That was from 1970 all the way to about 2010. But you can see that the growing here is going good. Like this is the clock speed in megahertz. And we started from below 1 megahertz in 1970 all the way in 2005. We have more than 1,000 megahertz, which is 1 gigahertz. Unfortunately, you can see that this rate is decreasing in the last few years in this figure. And you can see that it's stopping here about 3 gigahertz. And this is actually the common BC's speed right now. So if you have a car, commonly it's about 3 to 4 gigahertz. Here in this plot, we have different processors. As you can see, the last one of them is the triangle one here with many versions. They are the Core 2 or Core 2 Do at that time, and they were reaching about 3 gigahertz. Up to date, up to this day, no processor achieved more than 10,000 megahertz, which is 10 gigahertz. So you shouldn't expect a workstation or a PC that you can buy for your office or home, and it has more than 10 gigahertz. This is including the liquid cooling and the boosting modes and everything else. And there is also some websites that's having records of what's going on and what is the fastest computer yet. Maybe they will break this line, but currently this is our record. It's below 10,000 megahertz or simply 10 gigahertz. We are actually reaching the atomic size. When we talk about the feature size, we said that it's reducing or going down throughout the years. So this plot is from 97 to about 2015. And there are several scientific research currently discussing less than 5 nanometer, which is up to 1 nanometer, as we said before. If you can see here, so just to make sense of it, this is one bacteria size. This, if we want to depict its size, and we assume that it's this circle size, in the 10 micrometer generation in 1971, and that was used in the 8008 Intel processor. You can see that it was this big, which is basically this blue circle. We couldn't draw the whole thing because we don't have enough space in this slide. But you can compare this to the bacteria or to this, for example, blood cell, as you can see. This is the red blood cell. Or you can compare it to the HIV virus. And you can see that it was huge at that time. We have reduced the feature size throughout the years, going to 3 micrometer, the orange circle, to 1.5. That's the pink circle, 1 micron, 800 nanometer, and so on. You can see that the sizes of these transistors are getting lower and lower up to a very simple dot. You can see it here. Even the compared to the HIV virus is very, very small. And that was in 2015, which basically is the 11 nanometer generation. Going below this, you will have a smaller and smaller atomic sizes. Going through the years, we have challenges. So from the CMOS that we will cover later, we have new techniques, and basically these are what are used today. We have the planar FET, the FinFET, the GA FET, and we have the MBC FET. So this is the planar, the FinFET, and the gate-all-around, or the GA FET. These are, you can see that the changes here is it's very similar to the model that we showed to you, but here we have certain widths, certain new designs for the transistors. Now, the gate, block, and chip costs and the cost of the technology scales. So scaling means more transistor density in the same area, which means you will have more transistor in a chip. You'll have more functionality, more gates, more blocks, more functions. And because you have the offer, or you have a lot of transistor that you can work with, each transistor will be cheaper with time. So the cost per gate or block or function is actually falling, because you have more functions that are fabricated in the same fabrication area, and you can work with them. I mean, we flooded the market with these transistors, so the prices are going down. At each new technology, or at each new generation, each gate costs about half what it cost in the previous generation, which is good. Things are getting cheaper. But if you look at the market today, things are getting more expensive. There are many factors related to this, but from our cost point of view, this growth in the chip cost is because of the integration troubles, the verification troubles, the testing, and the low yield. Because of this problem, we need to hire more engineers, we need to have more research, we need to spend money to go around some of the problems, because we are reaching to the atomic scale, as we mentioned, and these are actually making the prices go up. This is not the only reason, there are many reasons, but from our point of view, these are good to mention reasons. So to understand costs, or how to calculate the cost of chips, we have a unit cost, which is the monetary cost or the monetary value of manufacturing each copy of the system, excluding the NRE cost. The NRE cost is the non-recurring engineering cost, which is one-time monetary cost of designing the system. You pay it only once, and that's it. So if you want to calculate the total cost of what you are producing in your lab or in your company, you will add this NRE cost to the total number of units cost that you have, which is the unit cost multiplied by the number of units. And from this, we can calculate the per product cost per number of units, which is the total cost in the numerator, which is this one, divided by the number of units. So you want to divide this total cost among all of the units. So you can do some mathematical manipulation here, and you find out that it's actually then NRE cost divided by the number of units plus the unit cost. So it's the unit cost plus something. And this something is because if you are distributing this NRE cost among the units. this is an example. If the NRE cost is $2,000 and each unit is $100, for 10 units, the total cost will be this 2,000 plus 10 multiplied by the $100, which is basically $3,000. Now, if you want to calculate the per product cost, so you will divide or this total cost, which is the 3,000, by the number of units, which is the 10 units, or you apply this equation, which is the 2,000 divided by 10 plus 100, which equals to $300. Now, remember in the question, we said that the unit cost is only $100. Now, because of this high NRE cost, we have $300 for each unit. That was the cost for each unit. Amortizing the NRE cost over the units results in an additional $200 to the original 100, which brings us to $300 per unit. Now, to make this efficient, you should have, or you should produce more, actually much more than only 10 units to hide this 2,000 cost among those units. And this is another subject of the cost. The feasibility study always think about this and other studies as well. Now, at this level, we will talk about the introduction to CMOS transistor. So now we will talk more about transistor and how to work with them. So we have the silicon lattice. All transistors are built using silicon. So transistors are built on a silicon substrate. Silicon is actually in group number 4. This is a group 4 material, which is here, as you can see. This is group number 4. And from the crystal lattice, it has bonds for 4 neighbors. This is why it's in the 4th group. And as you can see, this is like, for example, the silicon atoms. And you can see the bonds, and each silicon have 4 bonds, 1, 2, 3, and 4. We like the silicon because we can make it conduct or insulate current easily, which means that the silicon is a semiconductor. So pure silicon has no free carriers and conducts the current poorly. To add or increase this conductivity, we need to add dopants. Those dopants, they will be either from group number 5, which are the donors, group number 5 being this part, or group number 3, which is the acceptors, being this part. Now, if you have, if you add the dopant from the donors, you will have an extra electron, which is the N-type transistor. We will build the N-type transistor using this. But up to this point, we will have an N-type because you have an extra electron. And to do this, you will have those 2 materials. These are good candidates, either arsenic, the As, or the phosphorus, the P. So this is from the donor, from group number 5, and you can see that this is the phosphorus, and this is the arsenic. Now, the acceptors, it's missing an electron, which is called hole or B-type, and they are from the acceptor column or the group number 3. The famous ones are the boron and the gallium. We can't use the aluminum because it's conductors. So it's the boron or the gallium. Now, as we said that the donors have an extra electron. So The extra electron is this electron that is very close to the silicon. So yes, it has a positive sign. The arsenic has a positive sign, but the free electron here is the one tied to the silicon. So you have the 4 bonds and you have a free electron. Similarly here, you are actually having a missing electron, which is represented by the hole or the plus sign here related to the silicon. Now, if we have a BN or if we have a B type and we connect it very close to an N type, we will have a BN junction, which is going to be between the B type and the N type, which forms a diode. The diodes allow the current to flow in one direction and prohibit the current to move to the other direction. We call this the anode and the cathode. And you can see for this configuration, the B type followed by the N type, this is the sample for it. You can see that the current is going to throw into the current will flow in this direction. And you can see it very clearly from the sample itself. Now the NMOS transistor, now we said that we can create the N type and the P type, or simply we call them here N plus, and here we will call it a P. And if we connect the N close to the P, we will have what we call the PN junction. So we have a PN junction here, we have PN junction actually all over the place because we have P all over here and we have N over here. So we have a PN junction here and here and here and so on. Similarly in the other region. If we connected N plus to the source, which is a region with an N plus type or the NN type, and we had connect another region to the drain, and we had a silicon oxide, which is an insulator between the gate and the rest of the transistor, we have what we call an NMOS transistor, which consists of gate, the source, and the drain, and the body terminals. These are 4 terminals. This is the source, gate, the drain, and the body is here. So the gate and the body are conductors. Usually they are conductors. The silicon oxide is a very good insulator. So there is no current. There's not supposed to be any current flowing through the gate. It's called a metal oxide semiconductor or a MOS capacitor, which means because you have like a region that allow currents to flow, another region here that allows the current to flow, but between them we have an insulator, and because of this we call it a capacitor, even though the gate is no longer made of metal. Now, metal gates actually are returning today, but that's another subject. Anyway, that was the NMOS transistor. Now let's try to understand how does it operate in a very simple manner. So the body is usually tied to the ground. So here the body is tied to the ground. When the gate is at low voltage, and this gate has low voltage or logic 0, the B-type body is at low voltage as well. So the source body and the drain body diodes are off. So these diodes that was created by the PN junction, both of them will be off. Now, because of this, you don't have any current that flow through the channels, and the transistor is off. You can look at it by the sample. This is the sample of the NMOS transistor. Now, if you have the transistor, the gate input of the transistor is logic 0, there is no current flowing between the source and the drain, which means the transistor is off. Now, if the input to this logic or to the gate is logic 1, now we have a voltage here. So we have a voltage difference between the gate and the body. So when the gate is at a high voltage, the positive charge of the gate of the inmost capacitor, the negative charge is attracted to the body. So you will collect the negative charges everywhere from the body to inside the channels, and you will start having connection between the source and the drain in this region, as you can see. This inverts the channel under the gate to an N-type, and now you have a current flow between the source and the drain, which means this transistor is on. You can remember this by the sample right away by remembering the active low and active high discussion that you had in a logic design course. So, because we don't have a bubble here, this is an active high, which means the logic 1 will make the transistor on. Similarly, if you have 0, as we discussed in the previous slide, now this will make this transistor off because you don't have a bubble here. Now, for the PMOS transistor, it's similar, but the doping and the voltage now are reversed. So we have a P plus here, P plus here, and we have N. And this is the sample of the PMOS transistor. So the body is tied to the high voltage, or usually VDD. You have the gate low, or if you have the gate low, then the transistor is on. If it is high, then the transistor is off, and this is indicated by the bubble, as I mentioned. So if you know that if you have a bubble here, then this is an active low design or gate, let me say. So also in our case, when this bubble means that this transistor, if you input 0 to the gate, then the transistor is on. If you input 1 to the gate, then the transistor is off. Now the power supply voltage, the ground is always 0. In the 1980, the VDD is 5 volts. Now the VDD has decreased in modern processors, and it's high. VDD would damage the modern time transistor. This is why you need to decrease it at every generation. So it's getting lower and lower in the generation, starting with 5 volts, then 3.3, 2.5, 1.8, 1.5, all the way, and we are reaching to the 1 voltage and even less than 1 voltage. Now this is what we actually need from transistors. We want the transistor to work as switches. That's the main goal. So if you found any other technology that behave as switches where you can make this part on or off, then it can work with computers in general. So we can fuse the MOS transistor as electrically controlled switches, as we said. Now in the NMOS and the PMOS, this is the conclusion of what we discussed. Now, if in the NMOS you have in the gate 0, then it is off. If it is 1, then it is on. For the PMOS transistor indicated by the bubble, if it is 0, then it is active, low, which makes it on. If it is 1, then it is off. Now, what if we connect them, connect these transistors in series or in parallel? Now, remember, in MOS, if you have 1 in the gate, it's on. The PMOS, if you have 0 in the gate, then it is on. Now, for the series in general, both must be on, so the path is connected between 2 terminals. In the parallel, either can be on to have a path. To explain this in a better way, let's see in this figure, you have 2 transistors, 2 NMOS transistors in series. So to have a path from A to B, both of them must be on, which means you have to have 1 and 1 here to have a path from A to B. Any other scenario, you will have a disconnection in the path and there won't be any connection between A and P, so we call it an off path. Now, for the PMOS, it's a similar case, but now both of them must be 0 to have the connection from A to B. Otherwise, you won't have a connection. Now, in the parallel case for the NMOS, one of them, if it is 1, then you will have a connection between A and B. You won't have a connection only in one case. That is when both of them are 0 in the gate. So when both inputs in the gates are 0, you don't have a path between A and B, and the path is off. Otherwise, it would be on because one of them would be 1. In the PMOS, we have the same discussion, but now the case where you don't have a connection from A to B is when you have 1, 1, which is this one. So it would be off. Otherwise, you will have one of the path is on when it is 0. So this is an on, this is an on. Or if you're lucky, both of them is on. So you have a connection between A and B. This discussion from series or the series and parallel discussion is very important to understand the CMOS design. And to understand this better, let's have examples. So this is the CMOS inverter. The CMOS inverter, if you have A is equal to 0, Y should be 1. If you have A is equal to 1, the Y should be 0. How is this happening in the design? Now, what we are doing is an analysis of this gate. I didn't tell you yet how to design. But suppose that I said that this is an inverter design of what you know in the logic design. How to test this from what we've just studied. What we are going to do is build the truth table step by step. So let's input 1 here in A. What will happen is one of these transistors will be on and the other will be off. Which one is on? Remember the bubble meaning that 0 is making the PMOS on. Since you don't have a bubble here, then the 1 is making this transistor on. Since we have a 1, so this is on and this is off. And now we can say that now the output will have, or this Y, have a path to the ground. Remember, the gate have no current flow. So there is no current flow in this direction or this direction. So since Y have a connection to the ground, the value of Y will be 0. The value of Y will be 0. Now, let's do the same for or try to complete the truth table. So for the other combination, which is the A being 0, and in this case, we have this transistor on and the transistor, that was the PMOS transistor, and the NMOS would be off. And from that, the Y is actually connected to the VDD, and because of this, the value of Y is logic 1, indicated by the one that we have in the truth table. And from the truth table, we surely know that this is really the inverter and this design is correct. Now, what we've done here is the analysis of the inverter, but how to build it? Is there a way to build the inverter or any other gate? Yes, there is the complementary CMOS model that we discussed or we showed to you before. Now we are telling you that we will have the inputs connected to the gates of the transistors only. And we will have 2 regions, the pull-up region or the pull-up network. Here we have only PMOS, and it is connected to the VDD in one part and to the output in the other part. We have also the other region, the pull-down network, which consists of only NMOS. and it is connected in the ground in one part and into the output in another part. So as you can see, the input is fanning out to the gate inputs of the transistors, and the output is fanning in from the pull up and the pull down network together. So this is called the CMOS design, or sometimes we have a distinction of saying it's a static CMOS design when we mention other circuits like the dynamic circuits, and we will discuss them inshallah. We'll discuss them inshallah later. So we have a pull down. Since we have two networks, so let's have all of the possible, or all of the combination, and let's see if there are some of them are possible or not. So if we say that we have pull down and pull up, the pull down in the rows and the pull ups in the columns, if we have the off, if the pull down is off and the pull up is on, so this is off and this is on. So we have a VDD in the output, which is logic 1. If we have pull down is on and the pull up is off, so the output is connected to the ground, and we have a logic 0. Now, what if both of them are off? So we have an off and off. So this could happen rarely. If that's the case, then the output's in the floating state or high impedance, or we call it Z. But if both networks are on, so now we have a competition. So basically what happens to this node is the VDD charge it, and at the same time, the ground is discharging it. So you are charging and discharging. So there is a fight between the pull-up network and the pull-down network on this node. So because of this, the pull-down, when the pull-down is on and the pull-up is on, we have an unknown state. We call it don't care or a crowbar. And by the way, this is very dangerous. If you have both of them are on at the same time for a longer period of time, which means that you are connecting the VDD to the ground, and this is basically a short circuit. Now, conduction complements. The complementary CMOS gates, they are called complementary because this is the intention. If you have the pull down is on, the pull up supposed to be off, and vice versa. That's the idea. So as an example, the NAND gate, the design of the NAND gate, when we design, we have series CMOS transistors in the pull down network. And we have a parallel or the duality in the pull up network, which is the PMOS. So the rule of conduction here is the pull up network as complement of the pull down. When we say complement, we mean it's the duality, which basically means if they are series in the pull down, then it is parallel in the pull up. If the NMOS are series on the pull down, then the PMOS on the pull up are parallel. And that was what the case in the NAND or the two input NAND circuit. So let's analyze the circuits, because we are not really sure. Only because we have these series and we make them parallel on the top. That's it. We have an AND circuit. maybe you are not that sure yet. So let's do the same thing. Let's analyze this design. So we will take this and we will investigate if it's really the NAND gate. So we will have the truth table and we will do this. That's the NAND gate. By applying De Morgan law, it's the inverted input or gate. It's the same thing. So what happens is we'll have the first case, which is 0, 0. We will input 0, 0 in A and B. So if you have 0, 0, this 0, 0 will make this transistor off, which means the other part is on. Similarly, this will be off, which means the other part will be on. And from that, you have connection only to the VDD, which means that the output is 1. Now, let's do the same for the other combination. For 0 and 1, 0 and 1, this 0 is exactly the same as previously. So you have off and on, but now B is 1. So you have it on in the NMOS and off in the PMOS side. And from that, you don't have a connection to the ground. We have only one path to the VDD, and the output is 1. Similarly, if we flip everything, so A is 1 and B is 0, now you will have the same behavior where you have a path to the VDD. And because of this, the output is 1. Now, if A and B is equal to 0, both of them equal to 0 to 1. So you have A is equal to 1 and B is equal to 1. Now you have on, and this NMOS and this NMOS, both of them are on. And the counterpart in the PMOS side, both of them are off. And because of this, now only this combination, you have a path into the ground and the output is 0. And we know that this is the NAND truth table. So this is really the CMOS design of the 2-input NAND circuit. We can do the same for the NOR. The NOR is actually we have it parallel in the pull-down network. The NMOS will be parallel and the PMOS will be series. So how to design using a PMOS? The idea is like this. Let's take this example, which is the NOR, 2-input NOR circuit. The 2-input NOR circuits is basically A or B all bar. Now, in the design, we design in the pull-down network. We design in the pull-down network. And basically what we do in the pull-up, we make the duality. We make the duality. Which is, if they are parallel, they will be series. If they are series, they will be parallel in the pull-up network. Now what happens is, you need to make sure that your function have an all bar for all the function. I like to call it all bar. So you have A or B, all bar. Since you have this bar on top of all the function, now you can take what's beneath this bar, which is A or B, and if they are OR together, A and B are OR together, then they are parallel. If they are AND together, then they will be series. Because there is an OR between the A and B, we will have them parallel. And we will have the dual in the PMOS pull-up network. So since they are parallel, they will become series in the pull-up network. Now, why we need to make sure that you have an all bar? The reason is because when you have a path in the pull-down network, the output won't be 1. It will be 0 because you will connect to the ground. And since you are looking at the output when it is connected to the 0, and you are building your network in the pull down first, then you need to make sure of the full bar on top of your function. So if you have all bar, take whatever beneath the all bar and build it in the pull down network. If they have OR, you have parallel. If they are AND, then you have it in series. And let's have an example to make sure you understand what I said. So let's say if I said sketch a 4-input CMOS NOR gate. So now the function y is equal to A or B or C or D, all bar. Since we have the bar, right, we take the function beneath the bar or under the bar, A or B or C or D, all of them parallel. You make them parallel here. And by the way, to make transistor parallel, connect. So let me draw it again here so you understand what I mean. How to connect in parallel. You draw the transistor one by one. So you have A, B, C, and D. And for all of them, you connect one terminal together and you connect the other terminal together. And this way you made them better. That's the way to make them better. And as you can see here, they are really parallel. And because they are parallel in the pull down, you make them in series and the pull up network for the PMOS counterparts. If you were asked that to build 3-input NAND gate, now the function here is A and B and C all bar, or you could write it A, B, C. All bar. And because of this now, you have a full bar or an all bar on top of the function. You take whatever under the bar and you design it in series because you have AND, they will be in series on the pull down network. And you can have the counterpart in the PMOS network in parallel because you'll apply the duality. Here's more examples, and this is what we call the compound gate. So if you have this function as an example, y is equal A ANDed with B or C ANDed with D all bar. This is also called and or inverter because you have and another and then you follow this with or, and then the all inverter. And this is also named by AOI22. A for and, O for or, I for inverter, 2 and 2 because you have 2 and 2. That's the naming. But we won't face this a lot in our course. We always try to mention the function itself to understand better. So you have this example. To design this, you have all bar, right? You take what's under the bar, A ANDed with B or C ANDed with D. So the A and B, they will be in series. They are in series. And you can see it here. C and D, they are also series. Okay. Now we want them to be this group and this group, you want them to be in parallel. And to do this, you connect this and you connect this to have what we have here. This would be the pull-down network. Now, in the pull-up network, you will have the duality, which is if you have A and B in series, then they will be in parallel in the PMOS counterpart. The C and D, similarly, they will be parallel. Now, those two groups, they were in parallel. We want them to be in series. To have them in series, you will have one on top of the other. this example, we have the C and D on top of the A and B. You can do the other way around, like A and B on top of the C and D, and it would be correct. And now we take this part and we put it in the pull-up network. And of course, while if you practice enough, you can go from the function directly to this without going through the steps. And to draw it, you can draw the logic gate as you know in the logic design courses. However, you can see here that we don't have lines to connect here between the AND and the OR or the NOR. And the reason is because we are designing this in the CMOS level, and we call it a compound gate. And to show this in the logic level, we don't have any lines here to see that this is a whole unit. This is a compound gate. Also note that you have a bubble here indicating the bar. You have the OR indicating this OR, and you have two ANDs indicating the two ANDs. And from here, you can see also the name. AND OR inverter 2 and 2. Now, here's another example, which is if Y is equal to A or B or C, ANDed with D all bar. Now, because we have full bar, we have A and B and C in parallel, in series with the D in the pull-down network. Now, in the pull-up network, what was in parallel, it will be in series, and this part was in series with this part. Now they will be in parallel in the pull-up network. So you can see that the design is fairly easy in CMOS. Now, we'll talk about the signal strength. The strength of a signal is how close it's approximate the ideal voltage sources. So the VDD and the ground rails are usually the strongest. So we call the VDD the strong one, or the strong logic one, and we call the ground the strong logic 0. Now the NMOS, this is by the transistor design themselves. In the NMOS transistors, it passes strong 0, but it degrades or weakens a logic 1. Now the PMOS passes a strong 1, but degraded or weakened a logic 0. And because of this, the NMOS are best for a pull-down network, and the PMOS are best for the pull-up network. If you remember the inverter that we discussed, we see that the PMOS is in the top, and we have the NMOS in the bottom, because this is connected to the ground, and this is connected to the VDD, and those two connected to the output, and this is the input. Now you can see that the NMOS is connected to the ground, because when this is on, the output will pass to the ground, and we will have 0. And because of this, now the 0 will pass as a strong 0, because the property of the NMOS, it will pass a strong 0, which will be really good in our case. This is why we have the NMOS in the pull-down network. Now for the PMOS in the pull-up network, if we have a 1 in the output, this means that this is on and this is off. And because we have a 1 in remember, this is the inverter, so the input must be 0. But here's the 1, this one is connected to the VDD. And this is very nice for us, because we know that the PMOS passes a strong 1. Actually, from this discussion, you should remember the inverter when you think about which input is strong or degraded. Now, to remember this, we know that in the inverter, the PMOS is connected to the VDD or the logic one. So the PMOS passes strong one. We remember that the NMOS is connected to the ground or a logic 0. So the NMOS passes a strong 0. This is what you should remember. Now, because you know that the NMOS passes strong 0, it must degrade the 1 and the PMOS degrade the 0. Now, we call the NMOS and the PMOS as a category or a classification pass transistors, because they really pass the value between the source and the drain based on the value of the gate. So if the gate is 0, there is no connection. So let's take this out. This is for the NMOS. For the PMOS, if the gate is 1, it is on. So let's take it out. Now, if it is on in the NMOS, so the gate is equal to 1. Now the source could have any value. We call this the input and the output. So the input and the output, when the gate is equal to 1, which is this case, we have two possibilities. This is the first possibility, and this is the second possibility. The first possibility is when the gate is equal to 1 and the input is 0. Since this is NMOS, remember the inverter, it's connected to the ground. Since the input is 0, the output is a strong 0. Now the second case, since it is 1, now it must be degraded. Similarly, here we have two cases. And now if the input is 0, it must be degraded. If it is 1, then it is a strong, because we know that the PMOS is connected to the pull-up network, which is connected to the VDD. So this must be the strong one in the output. Now, what do we mean by degraded? It means that, for example, if it is degraded 1, you know that the 1's supposed to be 5 volts, because this is the maximum voltage to you. The degraded logic 1 is not 5 volt, it's maybe 4.5 volt. So it's not really the full 5 volt, it's less than that. That's for the 1, for the logic 1. For the logic 0, you know that the 0 should be 0 volt. Now the degraded 0 is not 0 volt, it's slightly more than this, maybe half a volt. This is what we mean by the degradation. Now, this is the pass transistors. Now, from this discussion, there were many attempts to build better gates. So we had what is called transmission gate, where between A and B, you have both an NMOS and a PMOS to cover all sources of degradations, to make sure that the B is always strong. You have both possibilities in the same design. Notice that if you connected the gate to G, you have the G bar here. So if it is 0, then you have 1 here. If it is 1, then you have 0 here, which means that those transistors, either they are on together or off together. So let's have one of the cases. If it is 0, then this is 1. And because you have a 0 here and a 1 here, this is off and this is off. So both of them are off, or the transmission gate all together is off. If it is 1 and 0, then this is on and this is on, and both of them are on, or the transmission gate is basically on. So why we have two, when the transmission gate is on, why having two paths between A and B? Because one of them will be strong and the other will be degraded, and this way we always make sure that the B is always strong. So let's have this. As I said, if it is the G is 0 and the GB, the G bar must be, the GB bar must be 1, and this is off. Both of them are off. For this case, when it is on, there is a path between the A and B. And because we covered both of them, if you have a 0 in the A, it will be zero, a strong 0 in the output. Or let me say it in another way. If you have a 0 in the input, it will be strong 0 in the output. If you have a 1 in the input, then it will be strong 1 in the output. Now, how is this happening? The reason is, if you have a 0 here, luckily we have NMOS, so it will be strongly passing to B. If you have a 1, luckily also we have a PMOS, and it will be strongly passing to the B. By including both of them in the design, or what we call the transmission gate, we gain advantage of both worlds. So we always have strong outputs. There is different samples for the transmission gate, but because it's a small design, I usually like to draw it this way. So the design itself is this sample. The tri-state buffer. Now, the tri-state buffer have a Z, or a high impedance in the output in a certain combinations. So the buffer is actually passing the A to the output, or the A to the Y, only in the condition of what's the value of the enable. Now, since the enable here is active high, if it is 1, then A will pass to the output. If it is 0, there is no passing, which means the output is a high impedance, which is like what we fill in the Y column. Some people also like to draw it like this. So you have enable and you have enable bar connected in a bubble. So it reminds you about the active low and the active high scenario. Why did we discuss the tri-state here? Because we actually can design this by transmission gate. Just by naming this enable, and this one is enable bar. Now the A will pass to Y when the enable is 1. Otherwise, you don't have a passing between, or a path between A and B, and the output will be floating or Z, high impedance. This tri-state design, tri-state buffer design, is called a non-restoring tri-state. And the reason for this naming is because if you have a noise, let's say we have a glitch in the input, this glitch will pass out to the output, which is we don't want actually this to pass. So whatever noise you have in the input, it will pass, unfortunately, to the output. So it has only 2 transistors. The design is very simple, but it is not restoring or non-restoring. So the noise on A is passed on to the Y. Now we have another state, another design, which is the tri-state inverter. In the tri-state inverter, we have the inverter that we know. You can see the input here. This is the PMOS, and this is the NMOS. But we add to that 2 more transistors. One of them in the PMOS we connected to the enable bar, and the PMOS we connected to the enable. And this way, similar to what we've discussed, both of them, the enable and the enable bar, either they are going to be off or on. They will be off when the enable is 0. So this is 0, this would be 1. There will be this, which means that this is off and this is off, indicating this scenario. If this is 0 and this is 1, so this is on and this is on, which indicate this scenario. And you can see in this scenario, you have a path, and you have a path here, and the design became a simple inverter, where Y is equal to A bar. But if you don't, then the Y is definitely going to be floating or high impedance. That's the tri-state inverter. Now, the good part about the tri-state inverter is that it is actually restoring. It can produce a restored output. How? Now, because the Y is not getting its value from A, remember the A is going to the gates, and there is no flow through the metal oxide or through the silicon oxide. There is no flow of the current through the silicon oxide because it's actually an insulated region here and here. And because of this, the output is either going to be fed by the VDD or, and this actually is we called charging the output because it's connected to the VDD and you are charging the output with charges coming from the power supply, or if it is connected to the ground, then it is going to be discharging, or you are taking out the charges to the ground. And because of this, if you have a noise in the input, it's not going to show in the output because there is no direct connection between the input and the output. Yes, there will be some effect. Maybe if let's say that the A is equal to 1, which means this would be off and this is on. Because of the glitch, there will be some like increased discharging because you have this spike in the high, but at the end of the day, it's connected to the ground and the value would be 0 all the time. It's going to be leveled and there is no spike in the high or in the low. And this is why it is restoring tri-state inverter. Now we will see the multiplexer. If we assume 2-to-1 multiplexer, we know that the multiplexer, if you have a selection line with a single bit, then you have 2-to-1 multiplexer where you have D0 and D1 as inputs, and you choose between D0 and D1 based on the value of S. So if S is 0, the output would be D0, so we will copy this here, regardless of the value of D1. Because if it is 0, you will choose this. Now it is 1, you will choose the value of D1 into the output, or basically, you will choose, if it is 1, you will choose D1 in the output. And this is the multiplexing that you studied in the logic design course. Now, if you have a gate level multiplexer design where you have Y equal S D1 or S bar D0, remember the D0 when the S is equal to 0, the D1 is when the S is equal to 1. When you design this using your previous courses in the logic design, you might design it this way. So you have S either 1 or 0, D0 is ANDed here, D1 is ANDed here, and you connect both of them into OR. To design this, the AND you will convert it to NAND followed by inverter, because we know that in the NAND we have 4 transistors, and the inverter we have 2 transistors. Similarly for this AND, we have 4 and 2. This inverter you have 2 transistors, and this OR we will convert it to the N node followed by inverter, and that's also 4 and 2. You can see 4 and 2 is equal to 6, 4 and 2 is equal to 6, and 4 and 2 is equal to 6, and this is 2 transistors. So the total is 6 multiplied by 3, 18 plus 2, 20. So you need 20 transistors. You need 20 transistors if you design like this. Now, we will design the multiplexers using transmission gates this way. Simply, we know that the transmission gate is passing or not passing based on the value of the gates. So if you connect S and S bar this way, and you flipped the connection in the gates in the other transmission gate, where you have S bar here and S here, notice that the polarities are different. If S is here and S bar is here, then it's the other way around in the other transmission gate. S bar is here and S is there. Now, in this case, if S is equal to 0, S bar is equal to 1, and based on this, this would be on, and this one is on, this one is off, and this one is off, and D0 will be selected into the output. If it is the other way around, if S is equal to 1, then this is 0, and this is 0, and this is 1. This will be off now, and this will be on, and D1 is chosen to be in the output. And this is basically a multiplex. And we did a 2-to-1 multiplexer with only 4 transistors compared to 20 in the previous slide. Okay, but again, the same problem. It's non-restoring design. So what to do? There are other ways of doing the multiplexing and making sure it is also restoring design. For example, we have an inverting mux. So the inverting mux, what you do is you apply the function as you studied. The multiplexing y is equal to S added with D1 or S bar added with D0. This is the multiplexing that we know. But now we will invert it to make an all bar or a full bar for this function. So to implement this function, which is the inverted mux, you do it this way. So those two series, they are series here. Those two are series, they are series here. And the two group are parallel, and they are parallel here. And we've seen this design before, but we changed the gate names. Now these series parts are parallel, and they pull up network. And this is basically the inverted multiplexer. This is just the multiplexer, but the output now is active. You can also draw it this way. And to see if this design is correct or not, you can analyze it the same way that we discussed before. Now we have the advantage of a restoring inverting mux. Now, if you want the multiplexer without the inversion, you simply add an inverter at the end, and you get the value. Now, a 4-to-1 multiplexer, you could do it this way. This is 2-to-1, 2-to-1, and 2-to-1. And there is a whole subject about building a larger multiplexer from lower or smaller multiplexers in logic design courses. Here it's very clear that you have D0, D1, D2, and D3 as the input because it's 4-to-1 multiplexer. You need 2 selection lines, S0 and S1. So for example, let's say that you have 1 and 0 here. And if you have 1 and 0, you will choose only one of these inputs, regardless of which one is it. In this case, if you have 1 and 0, so the 0, you'll select this and this. So you'll have the D0 bar, and you have D2 bar here. Notice the bubbles. Now, because you have 1, you will choose this one, and after the bubble would be D2. Now, we took advantage of this inverting multiplexer, and we get the right polarity that we want without having a bubble. So it's a restoring design with this multiplexer. Now, these ones, each one of them, you could design it this way. Or you could design the 4-to-1 multiplexer altogether like this. You can see that you have 4 selection lines, not 2, but 4 selection lines. Usually these 4 selection lines are coming from a decoder. The decoder should be 2 to 4 decoder, where you have 2 and 4 lines here. So you decode the inputs. Usually, if you are given 2 inputs, which is this 0 and this one of these lines would be 0 and the other will be, one of these lines would be 1 and the others will be 0. So if, for example, this is 1 and this is 0, 0, 0, so obviously you will choose D0. If this line is 1 and the other 0, then you will choose the other input and so on. This is the way. So notice that each one of them have, for example, if you have this 1, then after the inverter you have 0 and you have 1. So this would be active. The enable would be okay or on. So D0 will pass through this inverter. So now here the Y would be inverted. So the D0 will be D0, but after you choose it. Similarly for the other one. And you can see that here we make use of the tri-state inverter. And we know that the tri-state inverter could be a restoring design. Now we discussed basically the basics of the NMOS and the PMOS, the CMOS design, and the transmission gate and how to use them in different symbol designs. Later we will talk about sequential circuits, and it's good to give you some revision about what you studied in the latches and flip-flops. The D latch is simply when the clock equals 1, this is the sample of the latch, you have D and Q, and you have a clock. When the clock is 1, the latch is transparent, meaning that the D will show up in the Q. When the clock is 0, the latch is opaque, or it's latching the value, it's saving the value inside the latch, which means that the Q will be hold and it will have its old value regardless of the value of D. And then the timing diagram, this shows this very clearly. If the clock is 0, so you are latching, or let me say saving, or let me call it L, so you have it with the same name. So you are latching, or you could say storing, if you like. And if it is 1, then it is transparent. So when it is low, the Q doesn't see the D at all. It has its old value. So if the old value is low, you continue low. You change the value only when the clock is 1. When the clock is 1, now the output, check the input. The input being anything. For example, it's 0 and 1 and 0 and 1. You could have it anything. But at that time, when it is 1, now you look at D and you find D is 1, which means that the Q should be having the same value. It is transparent with a certain delay. Now, during the transparent phase, D is changing. So you copy the change in the output. Once the clock is low, so you are latching or saving, you no longer look at the changes in D at all. You save what you have before. Whatever the value, which is 0, you continue and have it the same value, which is, as you can see. Now, the latch design is basically simple. 2 inverters back to back, like this. That's the whole idea. So if you have 0 here, this inverter will have it as 1, and the 1 will be input here, and you will flip again to 0, to 1, 0, 1, 0, 1. So if you look at here, you will see 1 all the time. If you look at this connection, you will have 0 all the time. This way you save the value. But now we need to control this. To control it, we have the clock. We have the clock in a multiplexer. That's the whole idea. So you have the two inverter back to back, and you control this by the clock. If the clock is 1, you have the D transparent to the Q. If the clock is 0, then you will have this behavior, which is the flipping behavior, and you are saving the value inside. Now we chose this to be Q bar and this to be Q. You can design the multiplexer as we mentioned using transmission gates for transistors. 2 transmission gates or 4 transistors. Notice the polarity. If this is clock and this is clock bar, this is clock here and clock bar here. They are flipped here. Notice that if this is the NMOS and this is the PMOS, we flipped it here. This is the PMOS and this is the NMOS. Anyway, it's one way or the other. Either both of them are on, meaning this transmission gate is on and the other is off, or the other way around. In this case, D will be transparent to the Q because the clock would be 1, or this would be off and this would be on. In this case, the clock would be 0, meaning that the D will be saved inside the latch. To clarify this even further, this is what we have. If the clock is 1, it's transparent. So this is not connected. It's only transparent. If the clock is 0, so now there is no connection between the D and Q. It's not transparent any longer. It's actually opaque, and you are saving the value inside based on the timing diagram that we just discussed. Now, what about the D flip-flop? We know that the D flip-flop has an edge trigger behavior, either positive edge trigger or negative edge trigger. And we will focus on the master-slave flip-flops, which means that if we consider the positive edge, when the clock rises, which means this rising edge, then you have the transparent behavior only at this time. Any other, you are saving. So the output will look at the input only in the edge. In the beginning, it was 0 because it was saving an old value, 0. And at that time, when you have a rising, it looks at the input, oh, it's 1, so you change to 1. You never change this value until you have the next rising. The next rising, you check the D is low, then you go low in the output. Now, the design of the D flip-flop, you build it using a master and slave latches. So you have a latch and you have another latch. This is the first design of the latch, and this is the second design of the latch. The only thing that you should notice here that the polarities here are different. If you connected clock bar and clock bar and clock, this would be clock and clock bar, clock and clock bar. One design would be the positive edge trigger, the other would be the negative edge trigger. How to know this? The design of the flip-flop, the D flip-flop, you have 2 latches. One of them would be the master and the other would be the slave. Now you see the clock and you see its connection to the second latch. If it is 1, then it's positive edge trigger. You can see it's, I'm not saying 1, should. If the clock is going to the second latch with this normal polarity, there is no bar, then it is positive edge trigger, no bar. Now, if there is a clock bar, then it is negative edge trigger, or if there is a bar. Now, in this case, we have a clock going to the second latch. This is why we have clock, clock bar, clock, clock bar. And because of this, we have a positive edge trigger. And since we have a clock here, after the inversion, we have clock bar. Now, if you want a negative edge trigger, basically you take this inverter and you put it here. If you do that, you will have a negative edge flip. Now, this behavior, you can see that there is an intermediate value, QM, and because the first latch, if it flips, the other one, it will flop. It's basically the same slippers behavior or the flip-flop behavior. If the first one go tick, the other will go top. So here, if you have this, if you have the clock 0, you can see that this is passing transparent, and this is off. So this is passing, but the other one would be saving. So let me put it this way. This will pass, and the other one is saved. And when the clock is 1, the change from 0 to 1 is basically the change here, which is the rising. Now, at that point, at that exact transition, this one would be saving, and the other would be passing. So at that rising level, it's like this D will move to the Q. And this is basically the operation as we discussed in the timing diagram before. Now, one problem in the flip-flops is the racing condition. If you have two flip-flops or in a single flip-flop. But let's take this example. If you have a flip-flop and another flop, which is basically two flip-flops, meaning they'll have two latches here and two latches here. And if you assume that you have a clock here, and you want the same exact clock here, no matter what you do, one of them will be faster than the other. So in this example, Q1 will show up before Q2. This race condition could have some troubles, like the second flip-flop, if it fires late, then sees the first flip-flop change and capture its result, which calls the whole time failure or race condition. This always have a problem. Even if you think about it, you would love it if you have the same clocks coming to each flip-flop at the same exact time. Now, to get rid of this problem, we have what we call the non-overlapping clock. This behavior could be in the NMOS, this behavior could be in the latches or in the flip-flops. So to do this, what basically we are going to do is for example, here we have two latches. Let the first latch work with a clock, let's call it phi 2. The second latch works with completely different clock, which is phi 1. Now, if we have this means that we need to work on the design. It's not going to be the exact way of designing things that you studied in the logic design. The design would be slightly different. You need to think about it a little. And it's showing clearly if you study computer architecture. If you study computer architecture, you should have studied pipelining in the processor. And in the pipelining, you'll have multiple stages, and those stages between them, you have status registers or buffers. Those status registers, one of them would be in phi 1 and the other would be on phi 2. And this way you can deal with this racing problem. For example, you could define phi 1 to be like this, and phi 2 would be like this. Now, if you look closely, they are not the opposite. They are not the opposite. Notice that in this region, phi 1 is equal to 1, And also phi 2 is equal to 1. And because of this, we call them non-overlapping clocks. If they are overlapping, it's a behavior that we don't want to see. We don't want both phi 1 and phi 2 to be in the transparent case. If they are both transparent, then the D will move here all the way to the Q, and everything will be a mess. So what we want, as we discussed, we want the edge to show up. So here we have 0 and 0. This time, it's like a guard. So they are not overlapped. Phi 1 and phi 2, they are not overlapped. So you can see phi 2 is 1 in this side. Phi 1 is 1. Phi 2 is 1, 1, and 1, and they never overlap. So these guards, we want them, but if you have long period of guarding, this will affect the performance. So you should keep them as short as possible, and at the same time, long enough to have a good guard between phi 1 and phi 2. And you could define them this way. Phi 1 is 1, 0, 0, 0, meaning 1 and then 0, 0, 0. And phi 2 is 0, 0, 1, 1, which is 0, 0, and then 1, and then 0. So if you want to define them this way, you could define it, especially when we use tools, you define it that way. Now, let's talk about the stick diagram. We will have this discussion in the next video because it's very important. So we'll check it with other things in the next video.